Welcome back everyone. In this section we will learn about epoxides. Although technically epoxides are also ethers or cyclic ethers to be correct, but they are discussed separately because of their exceptional chemical reactivity. Epoxides are cyclic ethers in which oxygen is one of the atom of a three-membered cyclic ring structure. This is the simplest epoxide. And as we learned in previous section, the name of this cyclic ether or this epoxide is oxirane. It should be noted that only three-membered cyclic ethers are classified as epoxides. Other cyclic ethers are not included in this category. Simple epoxides are named as derivatives of oxirane. For example, this is oxirane because there are no substituent groups present at number 2 and number 3 carbon. But in case we have substituents present at number 2 and number 3 carbon, we still name them as derivatives of oxirane. So in this case, the name is cis-2,3-dimethyloxirane because we know that number 1 is always given to the oxygen, and then number 2 and 3 will go to the carbon atoms. Where epoxide is part of another ring system, it is shown by prefix epoxy. So for example, in this case, epoxide is part of a cyclohexane ring system. And in these kind of epoxide compounds, we use the prefix epoxy to signify that an epoxide ring, or that is the three-membered cyclic ring with oxygen is present. So therefore, name of this compound is 1,2-epoxy. This is the prefix for epoxide, and rest of the name is the usual cyclohexane name. So it's 1,2-epoxy cyclohexane. Common names of epoxides are derived from the names of alkene from which the epoxide is formally derived. For example, in case of oxirane, oxirane can be derived from ethylene. So if we add oxygen, so one of the bond breaks, so this will result in formation of a cyclic three-membered ring. So as we can see that oxirane is derived from ethylene, so therefore the name is ethylene oxide. Similarly, the second example given here, so this compound can be derived from 2-butene, so hence the epoxide name is cis-2-butene oxide. To be clear, this is not the synthesis scheme. I'm just making a point that the names of epoxides or the common names of epoxides are based on the alkene from which they are derived. So epoxides can be prepared from alkenes, but this is not the synthesis scheme as shown here. The correct synthesis reaction of epoxide is shown here. This reaction shows the synthesis of ethylene oxide or oxirane. Oxirane is one of the few epoxides which is manufactured on an industrial scale, and it is prepared by air oxidation of ethene. The common name for ethene is ethylene. So based on the common name of ethene, the common name of oxirane is ethylene oxide. This reaction takes place in presence of silver metal as a catalyst, and this method only works for synthesis of oxirane. Other epoxides cannot be prepared by this reaction scheme. In previous slide, we saw the most common industrial method to prepare epoxide. The most common lab method to prepare epoxides is the oxidation of an alkene using a peroxycarboxylic acid. These kinds of acids are also known as per acids. We know that normal carboxylic acids have a functional group in which carbon is covalently bonded to an oxygen atom with a double bond and an hydroxyl group. So this is a normal carboxylic acid. In percarboxylic acid or peroxycarboxylic acid, we have one additional oxygen atom. So instead of just the hydroxyl group, in peroxycarboxylic acid, we will have an oxygen in the middle of hydroxyl group. So this functional group is known as peroxycarboxylic acid functional group or peroxycarboxyl group. The three most commonly used peroxycarboxylic acid for synthesis of epoxides are metachloroperoxybenzoic acid, which is abbreviated as MCPBA, or magnesium monoperoxyphthalate, it is abbreviated as MMPP, or the third one is peroxyacetic acid. It is also known as peracetic acid. An example of epoxidation of alkenes is shown here. In this reaction, cyclohexene reacts with a peroxycarboxylic acid and this reaction takes place in presence of dichloromethane as solvent, and the resulting product is a 1,2 epoxy cyclohexane. The peroxycarboxylic acid changes to normal carboxylic acid. As we can see from the product that the reaction is stereospecific, and the stereochemistry of the product depends on the stereochemistry of starting material. In this case, our alkene is a cis alkene because both hydrogens are on one side, so this is a cis alkene. So hence our epoxide group is, or epoxy group is also in sort of kind of a cis configuration. We'll discuss more about stereochemistry in next slide. Discussed earlier, epoxidation of alkenes is a stereospecific reaction, and the stereochemistry of products depend on the stereochemistry of reactants. Epoxidation of cis alkenes give only cis 2,3-dialkyl oxyranes. So in other words, if we start with a cis alkene, our product epoxide will also have a cis configuration. For example, this is a cis 2-butene, and in this case, if we conduct the epoxidation reaction, the product will be either the epoxidation can take place on the top half of the alkene, so it's a flat planar molecule. So the oxygen can be added to the top of the alkene. If that happens, then our configuration will be this one, or the epoxidation or oxygen addition can also take place on the bottom side. In that case, the configuration of this alkene will be in both of these cases, these are same molecule. So hence we get only one product, and this is a cis product, or cis product, cis oxidane. Now let's take a look at when we start with trans 2-butene. So if we conduct the experiment with a trans starting material, in this case our products are no longer same molecule. In fact, they are pair of enantiomers. So the product in this case is trans 2,3-dimethyl oxidane, and these are pair of enantiomers. And these two are same molecule. As the stereochemistry of product is affected by the stereochemistry of the starting material, hence this reaction is stereospecific. Proposing a reaction mechanism for epoxidation of alkenes, two important facts must be taken into account. Fact number one is that this reaction takes place in presence of non-polar solvents, which mean that no ions are involved during the course of this reaction. This is extremely important fact because this indicates that carbocations or carboanions are not generated in this reaction mechanism. Hence, this reaction mechanism cannot be explained by usual SN1, SN2, or E1 or E2 kind of mechanism. The second fact is that this reaction is stereospecific, which retains the alkene configuration. This means that even though the pi bond is broken during this reaction, but there is no free rotation about the remaining sigma bond. So considering these two facts, a mechanism for alkene epoxidation was proposed, and the mechanism of this reaction is shown here. According to this mechanism, the bond making and bond breaking steps are concerted. That is, the bond making and bond breaking process takes place in a single step. According to this mechanism, the pi bond of alkene uh, attacks the oxygen atom and creates a sigma bond with the oxygen atom of peroxycarboxylic acid group, and at the same time the sigma bond between the two oxygen atoms shift and create a pi bond between carbon and oxygen, and the pi bond between carbon and oxygen creates a sigma bond with hydrogen, and the bond between hydrogen and oxygen creates another sigma bond with the neighboring carbon, and thus completing the cyclic three-membered ring, which is the epoxide. All of this bond making and bond breaking process take place in a single concerted step. Epoxides can also be synthesized from halohydrins. Halohydrins are compounds which contain halogen and hydroxyl group on adjacent carbons. We learned about halohydrins in alkene addition reactions. Halohydrins can be formed by reaction of halogen and water on alkenes. For example, if we react 1-propene with a halogen such as chlorine and water, it will result in formation of a halohydrin. And if the halogen is chloro, then the compound is a chlorohydrin. Halohydrins formed by addition reaction are racemic mixtures. And when halohydrins are reacted with a strong base such as sodium hydroxide in presence of water, they will result in formation of an epoxide. The mechanism of this reaction involves two steps. In step number 1, strong base removes the proton from the hydroxyl group of halohydrin. So sodium hydroxide acts as a base. So first step is a acid-base proton transfer. And this step will result in formation of an alkoxide ion within the halohydrin. As we know that alkoxide ion is a strong nucleophile, and chloro group is a good leaving group. Therefore, second step is an internal SN2 reaction in which the alkoxide ion within the halohydrin act as a nucleophile and the halogen act as a leaving group. So this will be an internal SN2 reaction, and it will result in formation of an epoxide. The name of this particular epoxide is methyl oxidane. As we learned in addition reactions of alkenes that halohydrin formation is both regioselective and stereoselective. For alkenes that show cis and trans isomerism, this reaction is also stereospecific. Conversion of halohydrin to epoxide is also stereoselective. So if we begin with a cis-2-butene to an epoxide by halohydrin method, we will only get cis-2-dimethyl oxidane. So let's account for this fact that why the cis-2-butene gives only the cis epoxide product. In this reaction, where cis-2-butene is converted to an epoxide, the reaction will take place in two steps. In first step, addition of chlorine and water to the double bond will result in formation of a halohydrin, and in the second step, the reaction with a strong base such as sodium hydroxide will convert that halohydrin to the epoxide. So if we write the reaction carefully from cis-2-butene and we consider all the stereochemical outcomes, we should be able to predict that why, or we should be able to figure out why this reaction gives only one product. So let's write this reaction step by step and we will consider all the stereochemical outcomes. So starting with the cis-2-butene, it is a flat planar molecule, and we know that addition of halohydrin to alkenes is an anti-addition process, which means that halogen and the hydroxyl group, they add on the opposite sides of the carbon-carbon double bond plane. So therefore, the first step, which is the addition of halogen and hydroxide, will result in two two different kind of molecules, and those will be pair of enantiomers. So in one case, chlorine is added on the left hand side, and hydroxyl group is added on the right hand side, and the other substituents and groups will behave accordingly. And the other enantiomer will be in which the chlorine is on the right hand side and hydroxyl group is on the left hand side, and you will see that these two molecules are mirror images of each other, hence they are pair of enantiomers. So these are the only two regioselective and stereoselective possible outcomes when this alkene cis-2-butene forms halohydrins. Now when we perform the second step, in the second step we add sodium hydroxide. So both of these halohydrins will react with sodium hydroxides. Let's call the left hand side halohydrin number 1 outcome, and then this one is number 2. So number 1 will result in formation of an internal nucleophile, and the other halohydrin will result in similar mirror image nucleophile. The final step is the uh, nucleophilic attack, and this attack, as we know, is intramolecular attack, in which the nucleophile attacks the neighboring carbon atom where the leaving group is present, and this leaving group leaves, and this results in formation of our final epoxide. In both cases, you will see that the resulting product is same. And same product is obtained in the second halohydrin also. So from this detailed reaction scheme, in which we considered all the stereoselective and regioselective outcomes, we can see that when cis-2-butene forms an epoxide, which is cis-2,3-dimethyl oxirane, only one outcome is possible. One of the most useful organic reactions discovered in last few decades is epoxidation of an allylic alcohol. This reaction was discovered by Professor Barry Sharpless, and hence it is known as Sharpless epoxidation reaction. The reagent used for this reaction is tertiary butyl hydroperoxide, titanium tetraisopropoxide, and diethyl tartrate. Diethyl tartrate molecule has two chiral centers in its structure, so therefore it has 2 to the 2 stereoisomers, which is 4 stereoisomers which can be there for this molecule. Out of these 4 stereoisomers, we have a pair of enantiomers and a meso compound. These pair of enantiomers are used as a catalyst in this reaction. We use either one of those enantiomer. We can either use this negative diethyl tartrate, or we can use with positive diethyl tartrate. Depending on what enantiomer we are using, the stereochemical outcome is controlled by this factor. In this reaction, tertiary butyl hydroperoxide acts as an oxidizing agent, and titanium tetraisopropoxide and the diethyl tartrate act as a catalyst. In chapter number 3, we learned that uh, an achiral starting material will always produce achiral product. But the beauty of Sharpless epoxidation reaction is that the end product is a chiral compound. It is an enantioselective reaction. So it means that we only get one pure enantiomer. So therefore, the end product will be a pure chiral product. Now, this is only possible because we are conducting this reaction in chiral environment. Our starting material is achiral. Our alcohol and tertiary butyl hydroperoxide both are achiral. There is no chiral center. But the reason why our outcome is enantioselective because our reaction environment, which consists of the catalyst, is chiral. So if we conduct any achiral reaction in chiral environment, the product will be a chiral product. So depending on what enantiomer of diethyl tartrate is being used, we can control the chirality of our product. If negative diethyl tartrate is used, then product A epoxide is obtained, and if we use a positive diethyl tartrate, then the epoxide B will be obtained. The structures of diethyl tartrate enantiomers are shown here. Earlier, we learned that ethers are not chemically reactive, so therefore ethers are not normally susceptible to be attacked by nucleophiles. The reactivity of epoxide is drastically different from the reactivity of ethers. To explain the reactivity of epoxides, we need to take a look at the molecular structure of these three-membered epoxides, that is oxyranes. In case of these three-membered cyclic ring structures, we know that in a triangle, the angles are 60 degrees. So that means this carbon atom has a bond angle of about 60 degrees. But we also know that both of these carbons are sp3 hybridized. And the ideal angle for sp3 hybridization is 109.5 degrees. Now we can see that there is a large difference in angle from the ideal value. Because of this enormous angle strain associated with the three-membered ring structure, these epoxides readily undergo a variety of ring opening reactions. Ring opening reactions take place to relieve this angle strain. A reference ring opening reaction is shown here. In these kind of ring opening reactions, a nucleophile will attack one of the carbon atom and the ether oxygen will act as a leaving group. So this will leave and it will result in a ring opening reaction of epoxide. One of the most common ring opening reaction of epoxide is the acid catalyzed ring opening by water. In presence of any acid catalyst such as sulfuric acid or hydrochloric acid, epoxides react with water to form glycols. Glycols is a common name for diols in which the hydroxyl groups are present on adjacent carbon. So the IUPAC name of this glycol is 1,2-ethane diol. Let's take a look at mechanism of this reaction. The mechanism of acid catalyzed ring opening reaction involves SN2 type of reaction mechanism. Let's take an example of ring opening reaction of oxyrane. In presence of water and an acid, it results in formation of 1,2-ethylene glycol. The step 1 of this reaction mechanism will involve a transfer of proton from the acid to the epoxide. As we can see that in this reaction, water is acting as a nucleophile, and the oxygen of epoxide is the leaving group, and oxygen itself is not a good leaving group. So transfer of proton from the acid will convert the ether oxygen to oxonium ion, and we know that oxonium ion is much better leaving group. This step will be a fast reversible step, and we will obtain a positively charged oxygen species which is known as oxonium ion. In step number 2, oxonium ion is attacked by water. Water is acting as a nucleophile, and this attack resembles the SN2 type of attack, and the nucleophilic attack takes place on the back side, and oxygen atom in oxonium ion leaves, and this results in formation of a new oxonium ion, and the ring also opens in this step. This step is not reversible, and this is similar to SN2. In the third and final step, a proton is transferred from the newly generated oxonium ion, which results in formation of a diol. As we can see from this reaction mechanism that the attack of nucleophile on a protonated epoxide shows an anti-stereoselectivity, which means that the leaving group and the nucleophile are added on the opposite sides. This behavior is a typical of SN2 reactions. So in SN2 type of reaction, the nucleophile attacks anti to the leaving hydroxyl group, and hence in this acid catalyzed ring opening reaction, the diols have a trans configuration. So therefore this product is a trans 1,2 ethane diol. As explained in previous slide in reaction mechanism step, that nucleophile attacks on epoxides at anti-position to the leaving group. Hence, the hydrolysis of epoxy cycloalkane always gives a trans 1,2-diol as a product. An example of this reaction is shown here, and in this reaction 1,2-epoxy cyclopentane undergoes a ring opening reaction, and it results in formation of a racemic mixture of trans 1,2-cyclopentane diol products. As we saw, that acid catalyzed ring opening reaction of epoxides result in formation of a trans diols. In chapter number 6, we also learned another method to prepare a diol. We learned that diols can be prepared by addition reaction of alkenes with osmium tetroxide. This reaction takes place in presence of a peroxide such as tertiary butyl peroxide, and the resulting diol is a syn addition product, or in other words, the diols which we obtain in this addition reaction is a cis diol. Also, in this chapter, we learned that alkenes can be converted to epoxides by using peroxycarboxylic acids, and this will produce an epoxide with cis configuration. The ring opening reaction of this epoxides proceeds by anti-addition or anti-attack by nucleophile. So therefore, this product or this reaction will result in formation of a trans product. So in the trans product, the two hydroxyl groups of diols will be on the opposite sides. We will get a pair of enantiomers so this addition reaction will give us a trans 1,2-cyclopentane diol. So now we can see that we can control the stereochemical outcome of this reaction by using appropriate reagents. If we want to synthesize a cis diol starting from an alkene, we can react that alkene with osmium tetroxide and it will result in formation of a cis product. But if we want to prepare a trans product or trans diol starting from the same alkene, we can convert that alkene to an epoxides, and then epoxide can undergo ring opening reaction to give us a trans diol. So we just learned the mechanism of ring opening reaction of epoxides using water as a nucleophile. In fact, water is not the only nucleophile. Any other nucleophile can give the same kind of ring opening reactions with epoxides. The value of epoxide is the variety of nucleophiles that will open the ring and combinations of functional group that can be prepared from them. So therefore, oxyranes can act as a starting material, and the ring opening reactions of oxyranes using different nucleophiles will result in formation of different uh, kinds of organic compounds with different functional groups. So this chart gives us an idea how, starting from the same epoxide, we can produce a different variety of organic compounds with different kinds of functional groups. So one common theme in all of these reactions is that they all will result in formation of an hydroxyl group, but along with the hydroxyl group, some other group, functional group, will also be present. So for example, if we use sulfhydryl group as a nucleophile, it will result in formation of a mercapto alcohol. In mercapto alcohol, we have a sulfhydryl group and hydroxyl group on adjacent carbons. Treatment of an epoxide with lithium aluminum hydride results in reduction of epoxide into an alcohol. Lithium aluminum hydride is similar to sodium borohydride, and both of these molecules are strong reducing agent. In this reaction, lithium aluminum hydride donates a hydride ion, and hydride ion is a strong base as well as a strong nucleophile. And this hydride ion will result in a nucleophilic ring opening reaction. The mechanism of this ring opening reaction is similar to the one which we saw earlier. So, and in presence of water, we get a proton here as well as the initial hydride which attacked the carbon atom will be present on. So this will be the alcohol. Now, if our starting epoxide is asymmetrical, in that case, the hydride from the lithium aluminum hydride will prefer to attack the less hindered carbon atom, and hence the resulting alcohol will have OH group present on the more hindered carbon atom. So hydride prefers less hindered carbon atom. Oxyrane epoxide, which is also known as ethylene oxide, is an extremely valuable building block for organic synthesis because each carbon of its two carbon skeleton has a functional group. This flowchart explains or shows how, starting from the same ethylene oxide unit, we can obtain different categories of organic compounds with various functional groups. In this flowchart, you will notice that reaction number 1 and reaction number 8, they use carbon-based nucleophiles, and hence these reactions result in elongation of carbon-carbon parent chain. So instead of two carbon parent chain in ethylene oxide, now we have a longer carbon chain. Reaction number 2 is a catalytic reduction in presence of metal. Just like carbon-carbon multiple bonds can be reduced with metal hydrogenation to alkanes, similarly carbon-nitrogen triple bond can also be reduced to carbon-nitrogen single bond, and hence in this reaction a cyanide functional group can be converted to primary amine functional group. Reaction number 3 and reaction number 4 are ring opening reaction by nitrogen nucleophiles, and reaction number 5 is an intermolecular dehydration reaction of diols, which results in formation of a cyclic ether. Epichlorohydrin is a chloro-substituted epoxide which contains one additional carbon atom, and that additional carbon atom is connected to a chloro group. Epichlorohydrin is a valuable building block because each of its three carbon contains a reactive functional group. For example, the carbon atom highlighted by yellow contains the chlorofunctional group, and carbon atoms highlighted by blue contains this oxygen functional group. Epichlorohydrin is synthesized from propene, and the reaction scheme of synthesis of epichlorohydrin is shown here. The first step of epichlorohydrin is a chlorination of one propene. This is a radical mechanism halogenation reaction, and at elevated temperatures such as 500 degrees Celsius, the product of this chlorination is not addition, but it's allelic substitution. The mechanism of this kind of reaction was discussed in chapter 8. Treating the haloalkene formed in step number 1 with a mixture of chlorine and water results in formation of a halohydrin product. So this is a simple addition reaction in which the halogen and water are added across the carbon-carbon double bond. The pi bond breaks and we obtain a halohydrin. So this chloro was already there, and additional chloro group is added when the pi bond breaks. So this kind of product is known as chlorohydrin. When we react chlorohydrin with calcium hydroxide, we obtain epichlorohydrin. This reaction is an internal SN2 reaction. This base removes the proton, and then the resulting anion, oxygen anion, attacks the carbon atom, and chloro group act as a leaving group, and this results in formation of epichlorohydrin. The characteristic structural feature of a product derived from epichlorohydrin is the 3-carbon unit with OH group in the middle carbon and nitrogen, carbon, oxygen or sulfur based nucleophiles on the 2 side carbons. An example of a compound derived from epichlorohydrin is nadolol. The structure of nadolol is shown here. So let me draw the structure. As we can clearly see, the epichloro backbone present in this molecule. Members of this class of compounds have received enormous clinical attention because of their effectiveness in treating hypertension. They are also used to treat glaucoma, migraine headaches, and some heart diseases. These categories of compounds can be synthesized from epichlorohydrin by using a nucleophile shown here and the other nucleophile shown here. So attack of these 2 nucleophiles will generate the desired nadolol class of molecule.